That was the Zombies singing Time of the Season, and you are listening to The Wild Side on Source 96.1 FM, and I am your host, Kight. And if you were listening last week, then you remember that I was talking about monsters, and zombies were just one of those monsters. But don't worry, I'm not out to scare you today. I'm not going to continue the monster theme. I actually am focused not on the artist in that song, but on the title of the song, and in this case, I'm going to be talking about seasons. As you all have noticed, we've recently undergone a real shift in season, and I know that it wasn't the equinox or the solstice recently, but we sure have had a week or two where all of a sudden it's really obvious that it's autumn, and all the leaves have been falling and the temperatures have been much cooler, and so I thought it would be a great time to sit back and think about why we have the seasons and what impact the seasons have on our lives. So first of all, why do we have the seasons? Well, you might think that this is a meteorological question because we associate the seasons with changes in temperatures and precipitation, but really it's more astronomical because these weather patterns are driven by what's happening in our solar system, and specifically what's happening with our Earth in respect to the Sun. So the Earth has an elliptical orbit, which means that it's kind of an oval shape rather than a nice precise circle. And as you all know, it takes about 365 and a quarter days to complete, and that quarter is what causes us to have leap years every 4 years. So while the Earth is orbiting the Sun, it's also spinning on its axis, and you all know that that is what causes the days. Well, the axis is not straight up and down; it's actually offset by about 23.5 degrees, and so that means that at different times of the day and at different times of the process around the Sun, you have this kind of wobble of the axis, of the Earth on its axis as it goes through its daily and yearly journey. And so that means that sometimes you've got the axis pointing towards the Sun, sometimes it's pointing away from the Sun, and that is what drives the seasons. So when an axis is pointing towards the Sun, then it's going to be summer for the hemisphere that's at that axis that's pointing towards the Sun. Conversely, when the axis is pointing away from the Sun, then it's going to be winter for that hemisphere. And the poles, because of this tilt, can never actually point directly at the Sun, but they're as close as possible to achieving this during the solstices. And the solstices are the 2 days of the year that are the longest. So first of all, solstice, just so you kind of understand where that word comes from, it means the sun stands, and it basically indicates that we've got this day when you've got a whole lot of sunlight just coming in perpetually, because the Sun basically seems, from our perspective, to stay in the same place for quite a long time, or at least to move very slowly. And these happen on approximately June 21st and December 21st, and then midway between the solstices you have a time when the axis is pointing 90 degrees away from the Sun, and this causes the equinoxes. And the equinoxes this word means equal night, and these happen when you've got approximately the same amount of day length as you have nighttime, so about 12 and 12. And I'm saying that all of these things are approximate because actually, first of all, the solstices and the equinoxes don't happen exactly on the 21st. It's kind of around in that area because you have to accommodate the fact that our calendars are not as scientifically and astronomically precise as our Earth is, and so it's more or less on those days. And you also have to take into account the fact that the equinox in particular happens when the geometric center of the Sun's disk crosses the equator. And that's not exactly on the same day when you've got light and dark exactly 12 hours apiece. So it's actually going to be different for different latitudes. But we just kind of use the 21st of March, which is the vernal equinox, and the 21st of September, which is the autumnal equinox, to kind of mark the turn of the season from one season to the next, because it's convenient to use the same date every time. So just to kind of get back to that whole point about the geometric center of the Sun's disk and the crossing of the equator, what happens is you've got this point remaining above the horizon for 12 hours everywhere on Earth when that geometric center crosses the equator. And the whole reason that the equinox focuses on the Sun's disk is because that's how sunrise and sunset are marked. So when you've got the leading edge of the Sun that rises above or falls below the horizon, that's when you've got sunrise and sunset. And it makes sense to pick this one fixed thing to measure these events every day, because when you think about it, the Sun is a big circle, And how are you going to say at which point of that circle's journey is going to be a sunrise or a sunset? If you just say it's when it comes up or when it goes down, different people might interpret that in different ways. And so astronomers have decided that it's when that leading edge actually moves across. And this actually can complicate things a little bit because it can be difficult to mark when that precise moment happens because we have atmospheric refraction. And that can be quite misleading because it makes it look as though the sun is rising earlier than it actually is because the light is being bent over across the horizon. And also it seems like it's setting later than it actually is because you have these remnants of sunlight that are, again, because of this bending process, they appear to us even though they're no longer actually there physically. Now something else that happens because of the tilt is that you've got the exact position of the sunrise and sunset changing throughout the year. And you might have seen photographs of this or little graphs showing this if you've ever taken astronomy. But it's quite interesting if you're the sort of person who kind of goes out and nature watches frequently. Then you might have gone to the same spot over and over again and looked out at the sunset throughout time. And you'll notice that from one day to the next, very slowly, you will see the sun shifting left and right across the horizon, depending on what point of the year it is. So relative to that fixed point, and let's just say, for the sake of kind of talking about it more easily, the fixed point is west, the sun is going to move from left to right throughout the year. And in the first half of the year, it's going to be to the right of west, which is northwest, if you are inclined to use cardinal directions, while in the second half of the year, it's going to be on the left of west, which is southwest. So to be even more specific, if you start at the vernal equinox, then kind of go throughout the year, the sun's going to move towards the northwest and then max out on June 21st, which is going to be the solstice, and then it's going to go back west towards back towards the west for the autumnal equinox, and then it's going to keep going and go southwest and max out on December 21st, and then go back towards the west and start all over again. And so you've got this movement right to left as you're staring at that fixed point throughout the year. And if you actually go out and take a series of photographs throughout the year, you'll have very nice evidence of how this happens. And this is the same for sunset and sunrise, only in that description you would change west to east in order to kind of understand how that movement would work. Now, these changes in proximity to the sun are not just kind of an interesting anecdote, but they're relevant because they alter the density of light per unit area on the ground. So you've got different areas of the world that are getting different amounts of light at different times of the year. And when the sun is directly overhead, in other words, when the axis is pointing towards the sun, so when you've got summer, you're going to have more light and heat directed towards a specific location. Whatever location you're interested in. So when the sun is lower then, when the axis is pointing away, when it's winter, if you're at that same spot, the light's going to be spread out over the surface of the earth relative to how it was before. It is actually something that you can do if you take a piece of paper and you have a flashlight and you kind of bend the paper around and move it at different distances from the flashlight and change the angle of the flashlight. And you'll notice that sometimes you have a really concentrated beam on the paper, and sometimes you have a very diffuse beam on the paper. And if you think about the fact that this beam is something that represents light and heat, you can kind of understand how this would have such a significant impact on the Earth. And actually, another experiment that you can do, which doesn't even involve having any equipment, is that you can just go out during the summer and the winter, and you'll notice that there's a change in the shadows during these times. So during the winter solstice, for example, the shadows are going to be really long at midday because the sun is so close to the horizon. But during the summer solstice, you'll notice that shadows are quite short, and that's because the sun is really high above the horizon. So factors like heat and energy and day length, all these things that are associated with the changing distance to the sun, the changing angle of the sun, these are all things, along with also the path of the rays through the atmosphere. Cumulatively, they combine to impact the weather. And they impact the weather by altering moisture content and temperature and driving changes in wind. And all this could be quite complex, and actually I am interested in talking about weather someday, but that's a topic for another day. But there's really one important pattern to kind of note in order to tie all of these things in to the seasons. And that's quite an interesting thing. That's another kind of experiment that you can do if you want to pay attention over the coming months. You might think that the solstices are going to be the most intense weather days because these are the longest days that we have. So you've got maybe the hottest and the coldest weather, depending on whether it's the longest in the summer, where you've got the most daylight hours, or the longest nighttime in the winter, when you think it's probably coldest because you've got the least amount of daylight. But actually that's not the case, because temperature results from this kind of complex reaction where you've got a certain amount of heat that the atmosphere receives from the sun, and also the amount of heat that we lose as energy is absorbed by the ground and the ocean. And so actually we're going to feel the hottest and coldest days when the ground and the oceans absorb enough heat so that they reach equilibrium with the temperature of the atmosphere. And so that's why you have this kind of subtle shifting into the seasons. So you've got this kind of autumn period and this kind of spring period where you're shifting from one extreme to the other. And that's because we're in the process of reaching that equilibrium. And then all of a sudden, once that's happened, you can feel those extremes of heat and those extremes of cold. And these same factors that I've mentioned here, things like heat and energy, the amount of radiation absorbed, which is the result of how long the day is, and also the path of the rays through the atmosphere. All of these, both directly and indirectly, can change lots of other interesting things that we associate with seasons. And after the break, I will talk about some of those things in a bit more detail. That was the lovely Tift Merritt singing Spring, and that is off of her new album. And today on The Wild Side we are talking about the seasons. Just before the break I promised that we would get into some of the science behind the interesting things that we associate with seasons. And one of these is maybe, other than the change in weather, the thing that comes to our mind most when we think about changing seasons, and it's something I've already mentioned once today, and that's the change in color that we see in the leaves of trees. And to understand why it is that this happens and how it is that it happens, you have to understand a little bit about the function of leaves. So you have to indulge me again. I'm going to go on a botanical trip. So chlorophyll, we all probably know, is a pigment that allows plants to absorb energy from light. And I mentioned this before when I was talking about coloration in the animal kingdom, because animals have lots of pigments, and I mentioned that chlorophyll was a green pigment that we see that's quite important in plants. And chlorophyll absorbs light in the kind of bluish range and a little bit in the reddish range, and it reflects light in the greenish area, and that's why we see leaves that are quite green, because those are the colors that it's not absorbing, and so they bounce back, and that's what we perceive. So the energy that's absorbed by chlorophyll allows plants to turn water, which comes from the ground, up from the roots, and also carbon dioxide from the air, into oxygen and sugar, and this is what plants store away in order to keep themselves happy and safe during the hard times, and also it's what they consume at any given time in order to kind of keep themselves running. So it's not energy effective for most plants to keep trying to do this during the winter because, as we've already discussed, there is less sun, the sun's farther away, they're just not getting as much, as high a density of light and energy as they need. And so it's better for them to just shut down and live off their stores that they've stocked away during the spring and the summer. Now, chlorophyll production is stimulated by light, so as light decreases, and this is something that happens with decreasing day length in autumn, we see that the plants stop producing chlorophyll. And the old chlorophyll is kind of depleting and dying out at the same rate as always, and so it starts to disappear from the leaves, and then there's nothing that comes in and replaces it, and this means that slowly we have this fading of the green color. Now, that explains part of the color change, but it doesn't explain why it is that suddenly we see these really vibrant hues. And that happens because chlorophyll is not the only pigment in leaves, it's just the dominant one. So with chlorophyll gone, you're able to see the other pigments that were there all along, and these include things like carotenoids and tannins. And there are also some pigments that increase at this time, so not only are you able to see what's already there, but you've got others that are being produced at a higher level, and so they start to kind of take over and really dominate. Now, in plants that have really high sugar concentrations, you will have the production of anthocyanin, which is something that produces a really vibrant red color. And this is something that's particularly impacted by light levels, because the more light you have, the more anthocyanin you have. And this can also be affected by the temperatures that you get at night, so whether it's quite cold or whether it's a bit more mild and warm. Now when you have less light, then you end up with having more yellowy and brown hues rather than that nice reddish color. And the relationship between sugar concentration and anthocyanin is why we have such amazing red colors in the American Northeast up in New England, because you've got all of those sugar maples, and sugar maples, of course, are named that for a reason, so they have all this sweet stuff inside, and they're able to use that to manufacture this incredible coloration. And the relative amounts of all these reds and yellows and browns are what determine the shade that different leaves will have. So sometimes you've got some that are purely red, sometimes you've got some that are purely yellow, and other times you've got about half and half, and that's where you get that nice orangey color. And this is why you have certain species that tend to have better fall foliage than others, but also in a single tree you might have some amount of variation. And that's because these different leaves are all a little bit different from each other, and so there might be kind of local variation in the pigments that are found in the leaves themselves. Now we know that animals also do kind of a similar thing to what a lot of plants do, and that is they kind of shut down during the winter, because just like with the plants, it's not always good for you to try to kind of stay awake and keep trying to find food during a time when actually food is very scarce. So for plants, food is difficult, or energy, if it's probably better to think about it as energy rather than food. It's difficult for them to come by this because the sunlight is so much less, and this can also be exacerbated by changing weather patterns. But with animals, what you find is that you've got a lot of snow, and so you have cold temperatures as well coming along with that. And so the animals that eat plants won't have access to the same amount of plants most of the time. And the animals that eat other animals will also not have access to those, because sometimes they get snowed in or iced in, and so they're not as active and they're not as easy to find. And so that's why you have a lot of species that prefer to go inactive and run off of their reserves, just like the plants are doing, especially the trees. And in the winter, we call this pattern of activity, or lack thereof, hibernation. And of course, you've already heard of hibernation. We see it in lots of different species, so things like squirrels and other little rodents. Bears are quite famous for this. Bats also hibernate. And during this time, what you're basically doing is just conserving your energy by kind of lowering all of your activity. And that includes the activities that are just involved in regular body maintenance. So you lower your temperature, you slow your breathing, and you also lower your metabolic rate. And all these things are kind of intermingled. And you see them to different degrees in different animals, because not every animal hibernates in exactly the same way. Now, a lot of people think that you have a lower body temperature in hibernating animals because it's colder outside, and that's actually not the case. What you find is that the animals have slowed their metabolism, and so that means they just don't have the energy to produce as much heat, and that's why you then have that lower body temperature. So really it's a result of what their own bodies are doing in order to prepare them to last for that whole time during those cold temperatures. And they're able to do this for such a long period of time because they're running off of their reserves. And in particular, that's body fat, because fat is something that's really good for providing the most energy per amount of kind of space, storage space that it takes up. And there are even particular types of body fat that work better than others at storing away and providing animals with this energy. And in order to put on all of that body fat, hibernation is generally preceded by a period of basically gorging, where the animals are storing their fat. And they can put on just massive amounts of weight during this time, and they can very easily even double or triple their body weight over this time, because they're putting on so much fat in order to last throughout the winter. But the length of hibernation actually does depend on lots of factors, and not all animals will stay asleep during the entire winter. So things like temperature and time of year, body condition, and also the animal's heat retention mechanism, so how much fur and fat it's been able to put on as a good layer to buffer against the cold. All of these things will determine whether the animal is hibernating for just a few days, for long weeks, or even months, for basically the entire season itself. So how is it that animals know when to hibernate? Well, this is actually something that's still a bit of a mystery, but blood of hibernators contains something called hibernation induction trigger. And analyses of this indicate that it contains something called a protease inhibitor, which is something that prevents proteins from being broken down, and also an opioid, which is similar to morphine. And so basically, you've got this chemical that goes throughout the body that kind of starts shutting things down little by little. And if you take an animal that has this in its blood and you take a blood sample and inject that blood into another animal, you can actually get it to go into sleep. It may not be as extreme a reaction, as extreme a hibernation as you might have in the other species that have, or sorry, the other individuals that have lots of this circulating, but you can still get this reaction to happen. And this is actually something that's of great interest in a medical setting, because if you can use these molecular processes in a medical circumstance, then you might actually be able to have some really beneficial effects on patients. And this is particularly interesting in the case of patients that are maybe like right on death's door. They've just had a heart attack and doctors need more time to work. If they could inject this into patients and kind of slow everything down and keep them sustained in that state for a while, then they might have more time to work on whatever they need to do in order to fix the person's system. Now in the summer you also have kind of a hibernation type event, only it's a bit different. First of all, it's known as estivation, so it has a completely different name. But also, in the summertime, you're not looking to run off your reserves and avoid unnecessary energy expenditure, but instead you're trying to avoid the risks that are associated with summer's weather, and that's things like high temperatures and really dry air, so you might desiccate. So as you might imagine, animals that are worried about high temperatures and desiccation are those that are generally associated with kind of watery environments, or they have quite moist skin and they're not very good at regulating how much water comes in and goes out. And so those are things like snails and crabs and crocodiles and salamanders. And all of these guys will also have estivation periods that kind of vary depending on the external conditions and also what they're capable of dealing with at any given time.